Hi guys, it's Manuel of Entagma. Today I want to introduce you to a subtle but interesting effect, a low poly transform. So I want to smoothly transform this high polygon sculpture here that I downloaded into its low poly representation. So I want to decimate this model, and then I want to build a setup to be able to blend between the two smoothly. I already prepared the starting file for you. I downloaded this bust here from a very nice website that is called My Mini Factory, or Scan the World, where you can download for free a lot of fine art 3D scans from different museums around the world. It's really a gorgeous site, and I downloaded this bust of Mary from Pieta from this site and used it for this tutorial. I first imported this scan, and it's huge and rotated 90 degrees such that it's facing down, so I transformed it to face upwards and stand on the ground plane. And then I created this null object and named it high poly just to have a point where the clean high poly mesh is coming out. And then I want to create a low poly representation of this model using the poly reduce. But instead of just reducing the polygons, I can use an attribute to tell the poly reduce where to put a lot of triangles and where to put large few triangles. And I do this by using the paint node. So I painted this red color here on the face and on the color here. And then I used this point wrangle to set the retention attribute. It's just the reciprocal of the green channel of this color. And then on the poly reduce, I can use this attribute to tell the node that it should reduce everything a lot, but where the color is, only a little. And by doing so, I get this low poly result here. And that is, so to speak, our target. So we want to transform this high poly sculpt into this low poly representation. So let's get started and do this effect. The very first thing we want to do is to reproject the vertices of this low poly model onto the high poly model to just get a perfect fit. Because by reducing the polygons, Houdini moved the vertices a little bit and we want to move them back. We can do this using a SDF volume of the original model. So let's create an SDF using VDBs by using VDB from polygons. Let's connect it to the high poly node, make it visible. And now let's use a smaller voxel size, say 0.004, and let's create a distance VDB, quite a detailed distance VDB. And we need some exterior band voxels because we want to use a gradient of this SDF to reproject the vertices. And at the moment, the VDB is only defined 3 voxels around the surface of the object, and that is not enough if the points are deviating more than 3 voxels. So let's set this to 30, and let's fill the entire interior, because we have to have SDF values wherever one of the low poly points is. And these settings make sure that we have values inside of the SDF everywhere. Now that we have this SDF, let's put down a null and call it SDF, just to clean up the setup. And now we can lay down a VOP, a point VOP, to reproject the low poly vertices. So connect the low poly vertices to the very first input of this point VOP, and let's call this reproject volumetric, like so. Make it visible. But before we dive inside, let's connect the SDF to the second port, because we need the SDF inside to be able to use its gradient. Now dive inside. To be able to reproject the incoming points, we both need the gradient of the SDF and the value of the SDF. The gradient is somehow the derivative of the SDF, giving us the direction to the closest point on the surface, or on the iso surface with value 0, and the sample, so the actual value, is the distance to the surface. We need both. So let's first get a volume gradient node and then a volume sample node. Volume sample node. And connect the file names of both to the second input, because the second input serves the SDF. And then we need to connect the position of the points to the sample position. So now the SDF is sampled wherever one of these points exists. And we get the gradient, which is a vector, and the volume sample, which is just a float value. Now we have to invert or negate the vectors of the gradient, because at the moment the gradient is pointing in the wrong direction, away from the surface. We need the vectors that are pointing to the surface because we want to reproject the points. So negate this vector. And now we have to scale this vector by using a multiply node. We have to scale this vector by the sampled values. And now we get a vector that is pointing to the closest point on the high poly surface and that has exactly the magnitude that is necessary to move these points to the surface. So we can now move the points by using an add node and adding these vectors to the incoming point positions, like so. And this sum goes to P. And as soon as I do this, these points snap to the high poly surface. So before we have that, after we have that. Now we have a more precise representation. To be able to do a smooth deformation, we need more points. So create a subdivide node and append it here to subdivide our model. But because everything is triangles, Catmull-Clark is not the right subdivision scheme. It is better to use OpenSubdiv loop because this is dealing with triangles a lot better, as you can see. Set the depth to 3 to get quite a lot of polygons. Now we have a lot of polygons, but everything is smooth because the loop subdivision scheme, like Catmull-Clark, smoothes the surface, and we don't want that. So we have to crease all the edges first before the subdivide. So let's lay down a point wrangle, call it set crease weight, and put it here before the subdivide. And inside of the Vex editor, we can just type add crease weight, which is an attribute that the subdivide understands by default, and let's set it to 20. Like so. And don't forget to set this wrangle to vertices. As soon as we do that, the subdivide understands the vertex attribute and stops smoothing the mesh, because we set this crease weight of 20 to all the vertices of the model. And so all the polygons still are sharp. If we disable wireframe, you see that we now have this result, and we need a normal to make the appearance nicer. So append a normal node, make it visible, set it to vertices, and let's set the cusp angle to 5, because we want to retain this sharp appearance of the original low poly, although we have a lot of polygons, like this. And now we have to store these normals, because we later on want to turn this into a smooth representation of the original model with different normals, and at the very end we have to blend the normals. So we now have to store the normals. That can be done with a wrangle too. So lay down a point wrangle, call it store vertex normal, like so. And let's create a vector attribute by typing v add and then my normal. That's the name I came up with. And let's set it to add n. That is the current normals. Switch the wrangle from points to vertices because we want to store the vertex normals. And now we have a nice low poly object that is in reality composed of very many polys, so it's a high poly looking as if it would be a low poly. And thus we can use this to blend smoothly to the real high poly object. So next, let's create the high poly version. It's important for the smooth version that it has exactly the same topology as this pseudo low poly version, because only if we have the exactly same topology we can blend between the two. So instead of using the original high poly, we want to create a new high poly out of this topology. And we can do that by just reusing our reproject volumetric. So just copy it by dragging it with Alt and append it here after this node. Make it visible. And it immediately reprojects all the vertices. It looks still very low poly, and that is due to the fact that the normals didn't change. So if I now append a second normal node here and set this to 180 to make everything smooth, you see that it now projected everything back onto the high poly. If I turn on wireframe, you see I have all the points here, but on the surface of the high poly. So now I have a facetted version and a smooth version. But the distribution of these polygons on the smooth version is not very pretty. Due to the fact that we reproject everything, we get a very uneven distribution of polygon sizes. So how can we fix this? Well, one idea is to iteratively smooth the surface and then reproject it again. Let's do that. So let's create a loop, a for loop with feedback. Put it here. And the very first step that we want to execute inside of the loop is the smoothing of this surface. So lay down an attribute blur. Let's connect it here. And you see that it is blurring or smoothing out the distribution of the polygons. I can go up with iteration, then you see that it's doing this a lot. But at the same time, it's moving the point away from the original surface. So what I want to do is to use this inside of the loop, but directly after doing this blur, I want to again reproject the blurred result to the surface, like so. So if I now connect this here at the block begin node, and then I go to the repeat end, and I will execute the entire loop 10 times, I get this result, a far better distribution of polygons. Just because in every step of the loop, the surface is smoothed, then reprojected again, then smoothed, then reprojected again. To get an even better result, let's up the iterations to 20. Wait a second until the loop finishes executing. And now you get this result, which is looking quite good. But here at the edges, I have a lot of stretching still. And that is due to the fact that I'm at the moment over-relaxing the surface. So if I go to the attribute blur, you see that the blur itself is doing 5 iterations in every step. And that is not good because it really should reproject after each Laplacian blurring step. So go down to 1 with this value. And this really gives a quite good result. So now what happens is that the polygons get blurred, deviating from the original surface, and then immediately after that they are reprojected to the surface. So instead of using the blurring iterations that are here directly on the blur node, I do a loop to be able to execute both iteratively, the blur and the reprojection. And after that I have the normal node, because without it I have still the sharp normals from the low poly version, and with the new normal node I now have smooth normals. So now I have 2 versions of my model. The very first one is this one, and the smooth one is that one. Both have the exactly same topology, same number of points, same number of primitives, but a very different appearance. Sharp and smooth. So what's left here is to again store the vertex normal, because we are planning on not only blending the positions of these 2 models, but the normals too. So append the store vertex normal here, but this time call it differently. So let's call it my smooth normal, like so. So after this node, we now have 2 normal attributes, one containing the sharp normals and one containing the smooth normals. Before we start blending between the 2, we need a falloff value. We need a value that tells where the facetted model should show up and where the smooth model should show up. And it would be nice if this falloff is not created on the high poly version, but on the real low poly version, one primitive at a time, because then the transformation will be snappy, one polygon at a time, and not too smooth. So instead of creating a falloff here, we go back up to our low poly version and create our falloff on this low poly. First we need a controlling object, so put down a sphere of type primitive. A primitive sphere in Houdini is defined by just one point. So if you make this visible, middle click on this node, you see it's just one point, which is the center of the sphere. Let's make the radius a little bit smaller. And directly after, append a transform to be able to move this sphere around, like so. Make the low poly visible, template this transform, press return over the viewport, and then you can move it up, like so. Here we have our falloff sphere. Now we need a VOP to create the actual falloff value. So lay down a primitive VOP, because we want to define the falloff for the primitives, not for the individual points, for this snappiness behavior. Connect this sphere to the second input, because it is the defining object, and the geometry to the first input. And call this falloff, and dive inside. First thing is to import the center point of this sphere. So let's import a point attribute and connect the file input of this import point to the second input, that is the sphere, and then quickly create a constant, set it to integer, and keep the default value to 0, and connect it here to the point number. Now we are importing point 0 of geometry stream 2, which is the center point of the sphere. To generate a falloff value, we can use a distance node. Let's calculate the distance between all the points of the model and this center point. And to get reasonable values, let's fit the result with a fit range. So at the moment, if the distance between the center point of the sphere and the currently processed point of the model is 0, then the falloff value will be 0. And if the distance is 1 or larger, the falloff value will be 1. We want the exactly opposite behavior. When the distance between the two is 0, we want a falloff value of 1, and if it is larger than 1, then we want a falloff value of 0. So just switch these values. To check if it's working, connect this to CD, go up one level, and quickly create an attribute delete and put it here before the falloff node. And let's delete the CD attribute on point level. That is necessary because as long as the point color is present, the primitive color does not show up. As soon as we delete this, we get the primitive color, and if we now move this sphere around, you can see that we have a nice falloff that is 1 inside of the sphere and 0 outside of the sphere, like so. Great. We can use that, but to use it, we have to bind export it, so create a bind export node to create an attribute from this falloff value and call it falloff, like so. Now we have a falloff value. But although it is created on the primitives, it's still varying quite smoothly if we move the sphere around, and that's because of the falloff range starting here at the center of the sphere and then going outwards until it reaches 1. So if we quickly go into the VOP again, we can up the source minimum to say 0.9, and by doing so, we are hardening the edge here, because now all the distances between 0 and 0.9 are just 1, and only the range between 0.9 and 1 is really transformed into a smooth falloff. So that is a far better result, because now we have really this snappy behavior that we seek. To be able to use this falloff value on our high poly version that we created earlier, we have to do two things. First, we have to promote these falloff values from primitive level to point level, because in the end we need a falloff value for all the points, for every individual point of the high poly version. And then we have to somehow transfer these values to the high poly version, because at the moment they are existent on this low poly model. One way to do that is, of course, attribute transfer. But it is distance-based and not very precise, and there is a better way. And this way is using primuv, so interpolating by using the barycentric coordinates. So let's use this way because it's more precise. But before we do that, let's lay down an attribute promote. Attribute promote. And let's just promote our falloff from primitive level to point level. Now we can use a node called attrib interpolate. And what this does is it uses two attributes on the geometry called source prim and source primuv. And these two are specifying the barycentric coordinates. The node is using these barycentric coordinates, so the coordinates inside of every primitive, to interpolate all the point attributes. It's a very handy node, but to use it, we first have to generate these two attributes, so the source prim and the source primuv. So what we have to do is we have to find a correspondence of all the points of the high version, so all of these points, to their low poly counterparts here. So we have to find the barycentric coordinates for all these points inside of these triangles. And that can be done, you guessed it, by using vex. So lay down a VOP, a point VOP. Call it find barycentrics, like so, and connect it here to this geometry stream, because we want to find the barycentrics for the high poly version. And we want to find the barycentrics on the low poly version. And the low poly version is actually this node here, because it contains the low poly version already reprojected to the high poly surface. So connect this to the second input. Now we have in the first input the high poly version and in the second input the low poly version. And now we can make this visible, dive inside, and use a function called xyz distance. And xyz distance can be used to gather the information we need. If we use the point of the high poly model as the position and geometry stream 2 as the input, it will find the closest point for every sample point on the low poly version. And it will not return the position, but it will instead return the primitive number that this point is on, and inside of this primitive a vector defining the coordinates relative to the polygon. And we can just bind these two values and use them with the attribute interpolate. So create a bind export and call it prim of type integer for the primitive number, and then a second bind export. Let's call it source primuv of type vector and connect it to primuv. Now we generated these two attributes. And these two attributes are the standard attributes that are here inside of the attribute interpolate node. And now that we have that, what we can do is we can use the output that we generated here, so all the high poly points with these two attributes, and we can use as a second input our low poly. And we did not call it source prim, but prim, so delete it here. Now it's not erroring out anymore. The color does not change, and that is because we only promoted the falloff value itself to point level. And as it is only interpolating the point attributes, it is not interpolating the color, but it is in fact interpolating the falloff. To make it visible, let's append a color node and use the mode ramp from attribute, put falloff here, make it visible, and now you see it's actually interpolating the low poly falloff value on all the points of the high poly object. So if I now go up and move this falloff around, you see that I have a falloff on the high poly object that has this snappy behavior because it fills one polygon at a time. And now let's use this to blend between the two versions. We'll do the blend using a VOP again, but before we do that, let's use some more descriptive colors here as a falloff, because black really is not very usable because you don't see the model anymore. So let's use pink. And now put down a VOP to blend, a point VOP, to blend between our two different results. So we want to blend this version, which is our interpolated low poly version, or the version that looks low poly, and as a second input we use our smooth version. So we have this faceted version and this smooth version. The faceted version contains the falloff value. Call this blend P, because this will blend the position. It is a point VOP. Make it visible, dive inside. To be able to mix here, we need not only the position from the first geometry stream, but the position from the second geometry stream, which can be imported with the import point attribute node, connected to the second geometry stream, and just use ptnum as the point number. This is by default getting P. And now we can use the mix node, and we can mix between the two vectors, so P and the imported P. But we need a bias, and this bias here is just our falloff value. So bind it to get it, put on a bind node, falloff. We'll bring in the falloff and we use this as a bias. And now we can use this blend value as a position. If we go up one level, you see that it worked. It's looking odd because we did not blend the normals yet. But if I for now switch to flat shaded, you see it's perfectly working. We have the faceted version on the top and we have the smooth version at the bottom. So that is good, but now let's care about the normals. And the normals are defined on vertex level. So we need the falloff on vertex level too. So before using a second VOP to blend the normals, let's promote the falloff from point level to vertex level. So lay down another attribute promote, append it after the blend, and let's promote the falloff from point level to vertex level, like so. And now we can lay down a vertex VOP, call it blend normals, and connect the smooth version to the second input port. Now dive inside. Now we're doing the same thing again. Let's import a value from the second geometry stream, but now it is a vertex attribute. So use second geometry stream for the file input and the vertex number for the vertex number input. And the attribute to import is called mySmoothNormal, because that is how we called it when we saved it with a wrangle. Now lay down a mix node and a bind node to bring in the falloff. Bring in the falloff. Now that it is on vertex level, it happily brings it in. And mix the normal of geometry stream 1 with the normal of geometry stream 2 using this bias, and the result goes to n. And as soon as you do that, everything is working. Although we are in smooth shaded, you see that we have this faceted look on top and the smooth look at the bottom. So the last thing is to get rid of the color. You can do this by using a color node, color everything white, like so. And now you have it, the low poly transform of this bust. If we now go up in our setup and move our falloff around, you can smoothly blend between the smooth version and the faceted version. So transforming a model to its low poly state smoothly. I hope you learned something today. That was quite a mouthful, using a lot of not so common nodes, but I think it's a nice setup and it serves as a basis for many interesting effects regarding transformations like these when we deal with identical topology but different looks. Thanks for watching and see you next time.
Let me say a very big thank you to all our patrons, especially Mohammed Al-Abri, Mikhail Ivanov, Rob Bryant Jr., Rafik Anadol, Chris Hebert, Nick, John Kunz and Joseph Howard. Thank you so much.